Today we're going to review chapters 1 through 3. In chapter 1, we talk about some basic concepts, most of which that you've heard in general chemistry. One thing that we want to consider is whether we have tetravalent, trivalent, divalent, and monovalent species. You want to get used to drawing these neutral forms of your elements. They go with the periodic table. Note the lone pairs on nitrogen and aluminum. If we take one step back, we also have a trivalent system with boron, although it has no lone pairs. So there's your basic setup for the elements that we're going to need to use in this course. How many electrons are owned relates to a species' formal charge. In this molecule, methanol, we look at electron counting and examine each atom to determine how many electrons are around them compared to their valency. With carbon, we know that this is supposed to have 4 bonds to be neutral. With oxygen, we need 2 bonds and 2 electron lone pairs to be neutral. So here we have no formal charges on the molecule. However, if we go to something like aluminum tetrahydride, remember that the neutral form has 3 bonds and 2 electrons. So when you go to the form that has 4 bonds to hydrogen, then you need to give it a negative charge. Let's go to another molecule as an example. Now we have to consider that oxygen has more bonds than it needs to be neutral. This is the acylium cation. So if you're going atom by atom, carbon has 4 bonds here, carbon has 4 bonds there, so carbon remains neutral, but oxygen has now 3 bonds and 1 pair of electron, so it gets a positive charge. If this exercise was hard for you, read section 1.4. It's critical that you get formal charges correct when you are drawing molecules. It's also critical that you remember electronegativity values. You don't have to memorize them, but you should be aware of their trends. And you should know that electronegativity increases as you go from down to up on the periodic table and as you go from left to right. I'll just jot down a few more. We don't need to go through the entirety of table 1.1, I think this is. But I'll focus on the atoms that we are going to use the most in this course. If the difference in electronegativity is less than 0.5, electrons are considered to be equally shared. So again, if the difference in electronegativity is less than 0.5, electronegativity, bonds are considered to be shared. How do bonds form? We're going to spend time in this class focusing on molecular orbital theory, so it's important to have a good grasp on this when we're considering how bonds form. Bonds form when you have an orbital that has one electron in it that encounters another orbital of a different atom that has another electron in it. And when they combine, you have a lower energy bonding orbital, and then that results in the creation of a higher bonding, that is unoccupied, antibonding orbital. Let's represent that bonding orbital in blue and draw what it looks like. Here we have constructive overlap of both of the orbitals. And in the antibonding orbital, we write this as a destructive overlap, so the orbitals are of different signs. Let's take a look at the molecule ethylene and consider the bonds that are in ethylene. we have a carbon atom, and 3 hydrogen atoms per carbon. Here, all of our orbitals are sigma bonds. The ones that are in blue represent sp3 hybridized orbitals. And the ones in green represent the 1s orbitals. And that's because hydrogen has an electron in its 1s orbital. When you have ethylene, then you need to form a pi bond between the 2 carbon atoms. So you still have your sigma bond framework with the sp3 hybridized orbital. You still have your sigma bond framework, but instead of sp3 hybridized orbitals, we now have sp2 hybridized orbitals. We have 1 s orbitals from the hydrogen, and now what we need to add to form that pi bond is 2 p orbitals. So these interact with constructive interference. Because the sp2 orbitals are shorter than sp3 hybridized orbitals, this CC bond is shorter than a CC bond. There. Similarly, a carbon triple bond is shorter than a carbon-carbon double bond. And I'm going to skip the molecular orbital image for that because you can find that in your book. It's important to remember VSEPR theory, that's valence shell electron pair repulsion theory. It's a very old, simple theory where we're just saying that electrons and bonds, which contain electrons, want to be farthest from each other as possible. So if you have a molecule like methane, you've got 4 bonds to hydrogen, and you want them to be in a tetrahedral arrangement so they can get far away from each other. So here we've got a tetrahedral arrangement. Ammonia also has a tetrahedral arrangement of electrons. But if you look at the atomic arrangement, what we have here is a pyramid. Another molecule with 3 bonds to 3 atoms is BF3. And note that in BF3 we don't have a lone electron pair on the boron. So here, boron just wants to get away from those fluorine atoms, and everything is in the same plane. This gives us a trigonal planar arrangement for electrons and atoms. Lastly, let's look at a simple example of water. Here we've got 2 lone pairs. So again, we have a tetrahedral arrangement of electrons, but now when we look at the atoms, we have a bent arrangement of the atoms. Oh, let's do one more example. BeH2. Here we've got no electrons, and that means that we have a linear molecule with a geometry of 180 degrees. If this was hard for you, see table 1.3. That is the end of the review for chapter 1. What have I done?